Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into the final section in Chapter 5 in the Big Ideas Math Integrated Math 1 textbook, Section 5.7, on systems of linear inequalities. Now, the whole chapter is supposed to have been on systems of equations. I did mention at the very beginning that at the end, systems of inequalities would pop up. Our section before was just graphing linear inequalities, and that was in preparation for this one. It's literally no different than what we did before. If we did the, if you followed along on 5.6, or if you understand how to do it, solid line versus dashed line, shade above or below, that kind of thing. Only now we got to provide two graphs in one. And actually, it strikes as a curiosity to me. I'm going to have to look it up right now and see. They used the phrase half shade before. I don't know if they can use the phrase quarter shade now or something like that. I never use the phrase half shade. I say shaded region or something like that. And here you're going to hear me say overlapping shaded region because there are going to be two things that are shaded and we got to find those. Use a pencil, please, for this stuff so you can do some erasing or darker shading as you go. Shade lightly to begin with, that kind of thing when you do it for yourself. Jump to the description section down below if you'd like to download some graph paper for yourself, the same kind of graph paper I'm going to use, scaling from -10 to 10 on both X and Y, as well as the PDF, of course, for the section as I begin with the lecture portion. Also check down below if you'd like to find the timestamps to any of these things. Go back to section 5.6, check out the playlist down below as well if you need to see the things on graphing linear inequalities, because I'm going to jump straight into it right now, understanding or assuming that you understand how to do that. Without further ado, I'm going to go ahead and get started. We're going to check solutions of systems of linear inequalities. So that means probably plugging in the X and Y and see if they make true statements. But remember, because it's a system, now it's more than one inequality there. It's not just a single one. We're going to graph systems of linear inequalities. To me, this is really the crux of it. Everything here. Write systems, maybe that's from actually having the systems there graphed. That doesn't necessarily sound like word problems yet. Real life problems always sounds like the word problems one. So we have all four of those. These are just phrases. They sound like what we said before, only now it says system of, system of, system of. So all that stuff before. Notice that they don't say half shade or quarter shade or anything like that anymore. I guess they can't say that now. So maybe they should have been saying shaded region like I have. I don't know. We'll see. Okay, system of linear inequalities looks like basically a system of linear equations, but with inequalities instead. So this and that graphed together. Now, unlike systems of equations where we found the point of intersection of the two lines, you have to remember that these two lines are not only the only set of solution parts here, sometimes they're not even the solutions. When it says y is less than x plus 2, that's a dashed line, so anything on the dashed line don't even count. But in the shaded region that we talk about, the overlapping shaded region of these will be the solution to the system. So it's not a single number. It's still an infinite number of solutions. Or there are no solution cases. We'll see if they pop up. But we're just basically going to graph them, not write ordered pair answers, unless they ask us to select them. So a solution to each inequality in the system. Obviously, the graphing will come into play in a second. We're going to start with seeing whether these ordered pairs are actually solutions to the system by straight substitution, not by graphing. So substitute 3 for x, 5 for y. You get 5 is less than 6, a true statement. So 3, 5 is a solution to the first inequality. In the second inequality, when you substitute it, you get 5 is greater than or equal to 4, also true. It needs to be true for both, not just one, to satisfy the system, and it does. Because both work, it is a solution of the system. It's not necessarily on, and it's not. It's not on the lines themselves, the boundary lines. It's inside their shaded regions, if we graphed it. -2, 0. Substitute -2 for x and 0 for y. Automatically, we see one that doesn't work. It's not even worth the check of the other, except to let you know through lecture portion that if one works and the other does not, that it doesn't make it a solution to the system. Being a solution to one isn't a solution to all. So if I'm doing problems, once I find out that one of them doesn't work, the first one, I'm not going to bother with the second one. It doesn't matter. Not a solution to the system. Not a solution to the system. Okay, graphing them, it's basically going to come out to be this. And I always contemplate how I need to do this for myself when I'm doing the graph things. I think they show up clear as day on their drawings. We'll see if they do on mine. But we're going to graph both of them on a single set of axes, right? So when we have something here, y is less than x plus 2, y is greater than 2x minus 1, here's this solid line, and we shade above the solid line, and then this dashed line, we shade below the dashed line. You can see what's red and blue as the unique portions of what's only a solution to one and a solution to the other. And this purple is what I would call, I don't know what they're going to call it. I got to find it, see if they actually say it. But they say the intersection of the half planes. Oh, that's great. I'm going to call it the overlapping shaded region. I guess that doesn't sound much shorter, but the overlapping shaded region. So right here is everything that makes a solution to this system of inequalities, anything inside the overlapping shaded region. That includes 0, 0. Now, I'm not going to actually literally test 0, 0 is an easy test. 0 is less than 2, 0 is greater than or equal to negative 1. But anything inside there is a solution to both, and that's what we need. So what I'm going to recommend you do, probably in a pencil format, is that even if you do some shading, like underneath blue and above red and whatever, that you truly darken what's here afterward in some sort of format. Obviously, I'm doing it in a very scattered kind of way right now. I know that there are some answer keys to things that won't even show the shading of these anymore, because these truly, what's in pure blue and what I'm calling red, what's in pure blue and pure red here, are not solutions to the system. They are now irrelevant. Only what mattered is what was the solution to the system, and that's inside here. So some of them will completely erase what's there, if you will. So you can erase that. Depends on kind of what your instructor would be asking of you. For my students, I would just ask to light shading for both, find the overlapping shaded region, and truly darken it. Now, the last thing I want to state here before we move on to their examples is that points on a solid line that bound the overlapping shaded region also constitute solutions to the system. Because you have to remember, points on the line itself would be solutions to the inequality greater than or equal to, like that. This would satisfy it, and it is underneath this blue dotted line. So this would count as a solution, whereas this would not count right here. A point on the dashed line. Doesn't matter whether it's bounding the overlapping shaded region or not, but points on the dashed line would not. Therefore, on this one, the point of intersection of the two lines does not count because of the dashed line. If it were solid, it would count, but only things inside the shaded region and with solid lines that bound the shaded region count as solutions. Okay, and I'm sure they're going to have us test points like that. If they're savvy enough, they're going to think about those kinds of questions. So we're going to graph these two as an example. Y is less than or equal to 3, y is greater than x plus 2. I'm not going to spend time talking about how they're graphed, like in whole, but this is the y is less than or equal to 3. A solid line for y equals 3 and shading underneath it, like so, in blue. And then in red, y is greater than x plus 2, slope of 1 and y-intercept of 2. The line is dashed and we shade above it as y is greater than. Excuse me. And then what's inside, essentially the purple right there, is the overlapping shaded region. Anything within there and bound by the solid line is considered a solution to the system. So they say they say graph it, and they say find the intersection of the half planes, one solution. They never truly requested to find a solution or determine what is a solution, but negative 3, 1 is an example of a solution without needing to test, although the test is shown right here that both do pan out. There are cases where you'll have no solution. You'll have no solution in it's simple like this. When you have parallel lines and you have shading below the lower line and shading above the bigger line, something like that, where there's no overlapping shaded region, right? Just because there's shading here and here. And this is a time where you might want to emphasize the shading itself and just show that it's there. And in showing the shading, you show there's nothing that overlaps, for sure. So there's no solution in this case here because there's nothing that would satisfy both inequalities at the same time. What's a solution to red will never be a solution to blue, and vice versa. So this is a no solution situation. Now you might say, what's an infinitely many solution situation? Well, pretty much any other one right here. This is infinitely many solutions right here, right? This goes on forever. You can plug in anything you want within the region. So there's no real infinitely many solutions that we speak on. And for the most part, we don't indicate single solutions unless they ask for what's a solution. There's never the solution, though. Writing a system, it's interesting that they're providing this now as far as writing a system, because there were questions on section 5.6 that did ask us to write the inequalities. So I'm just going to say it straight up like this. You're writing these as you know how to, meaning come up with the boundary line here and here, and come up with whether you shade above or below and whether it's dashed or solid. So for me on this one, this is y equals negative 2 as a boundary line. Y equals negative 2 because we're shading above it. And you can tell we're shading above. See, all they're showing here is the overlapping shaded region. Let me stress this. They're only showing the overlapping shaded region, which means the original shaded region of what would be, for that one, would be above here, like this, above the horizontal line. and then below the dashed line. Maybe that's a new portion that we'd have to talk about, right? So below the dashed line like that. So the overlapping, you probably can't see that very well, but the overlapping shaded region for those is above this and below that. That being said, we are above the horizontal. So above the horizontal is greater than, and because it's solid, it's or equal to. So this should be y is greater than or equal to -2, which is right there. In the other one, we have to identify the other one's boundary line, which is a y-intercept of 0 and a slope of 1. Y equals 1x plus 0 is better written as y equals x. Because it's dashed, that means it's either greater than or less than strictly, not equal to, and because it's shaded underneath it, then it's less than. So y is less than x is this other one. You can see. Whoops, you can see right there. Sorry if I was hiding the other ones to begin with, but they're there. So I'll make sure to do those. I'm sure those will be examples, so we'll get ready for this. Here's another example. This one here, we didn't do too many of these, just a couple of them, but this is a vertical line that's an x equals equation. So x equals 3 is that vertical line. It's not about shading above or below x's. It's about shading to the left or right of x's. As we know, less than is left. So we shade to the left of the x's. This should be x is less than or equal to 3 as one of your sets right there. Boom. The other one right here comes from the y-intercept of -1 and a slope of up 2 over 3. You got to establish some point that it hits. And like I said, I did this in section 5.6. But establish some points that they hit to identify slope. So this boundary line is y equals 2/3 x minus 1. Because we're shading above it, the y's will be greater than. So y is greater than 2/3 x minus 1, and it doesn't include it. So it's strictly greater than, not equal to. So y is greater than 2/3 x minus 1. There's our system. So they did two different examples there. We have yet to see real-life application, real-life problems. Okay, these are among my favorite kinds of word problems. Not like, oh, I love doing them, but they are the most tangible, hands-on, make sense of kinds of things. And I did mention that in section 5.6 as well. But systems, even better to me. You have at most 8 hours to spend at the mall and at the beach. You want to spend at least 2 hours at the mall and more than 4 hours at the beach. Now, I want to stress that we don't generally write systems of inequalities in real-world scenarios, but these will have real-life solutions that we can understand. Anyway, you want to spend at least 2 hours at the mall and more than 4 hours at the beach. Write and graph a system that represents the situation. How much time can you spend at each location? So you are going to have to define variables for these things, and they can get kind of interesting based on what we have. But at most 8 hours to spend at mall and beach. If x, I'm going to guess x is number of hours at the mall. Where are we? If x, here we go. If x is number of hours at the mall, y is number of hours at the beach, the sum of your hours cannot exceed 8. So it's less than or equal to 8. And then it says you want to spend at least 2 hours at the mall. So your x hours must be greater than or equal to 2. You're going to actually graph that. So x is greater than or equal to 2. And then more than 4 hours at the beach. That's not greater than or equal to, but more than, including 4 hours and 1 minute, like that kind of thing, right? So y is greater than 4. So when you graph the system, you can see it right here. Here's your x plus y is less than or equal to 8. Now what you're missing here is, of course, the arrows and the idea of what the whole less than or equal to would be right here. We're only going to be in the first quadrant for most of these word problems anyway. But we also are, especially based on how these x's and y's are limited to these positive sets, but we're shading underneath it basically. Then x has to be greater than or equal to 2, which is to the right of 2, and y is greater than 4, which is above 4. So the overlapping shaded region, this is kind of a poor man's way of me doing this, but overlapping shaded region of this, and this is that triangular region that you see within there. Underneath this one, to the right of this one, and above this one. And there you have it. That means anything within this shaded region represents a solution to what you want. You can't spend more than 8 hours total outside doing the mall and beach, whatever. More than 4 hours at the mall, at least 2 hours on the beach. So this can be a solution right here, which is 2.5 hours, for example. Oh, actually, they have one, literally. They do have 2.5. 2.5 hours at the mall, and then 5 hours at the beach is a solution to that. Right? It doesn't have to be exactly in the 8-hour range. That's kind of what I like about inequalities versus equations for that. And there it is. There's still an infinite number of solutions, kind of like that. It's just within that defined range. So those are ones that I like, and I do have other videos on those ones that I probably would encourage that you check out if you can find them. Systems of Inequalities by Mr. Robinson. Okay, vocabulary and core concept check. Let's begin that, and then we have 48 questions in total to do with this. Vocabulary. How can you verify that an ordered pair is a solution of a system of linear inequalities? You got to substitute them into each inequality and verify that they make true statements. So substitute the XY values into both into all inequalities of the system. There can be more than 2. We just saw that in the word problem. There were literally 3 of the system, and show that they make true statements. And again, true statements means it doesn't necessarily mean equal, like in the days that we got to check for equations. Now it's all about the less thans, the greater thans, or maybe equal to's. Those are possible. But that's our substitution. That's our check. And I'm sure our first problems are going to be all about that. You can, okay, that's one way. You can also check, I was about to say, you can also check in a graph, right? It's not just substituting. Also, in a graph, see if the point exists in the, what I call the overlapping shaded region, not the intersection of half planes, the overlapping shaded region, or on any solid line that bounds the overlapping shaded region. And I need to stress one more important part about that, actually, before I move forward. I did mention during the lecture portion that any point, like on this one here, and I don't know what they're going to ask us here yet, but any point that's on this portion here is considered a solution to the system, whereas any part here is not. I also need to mention that any part here is not. Just because it's on a solid line doesn't mean it's a solution to the system. It needs to bound the overlapping shaded region, and this part does not, whereas this part does. And of course, this part's a solution as well. So I think that's what they're going to ask here. It says, which one doesn't belong? Use the graph shown. Which of the order pairs does not belong? I think we're looking for things that are solutions versus things that are not, is my guess. So on this first one, 1, -2, we'll call that A and see where that belongs. 1, -2 is that's actually not a solution. So although it's the point of intersection of the lines I did mention, if one of them's a dashed line or both, then it's not a part of the solution set. Anything on a dashed line is never a solution. It needs to be in the region or on a solid line bounding it. So that's an A. 0, -4 is a solution here. That one's good. So I'll make that different. I'm assuming that's what we're differentiating between. -1, -6 also appears to be a solution here. So I'm guessing we're going to see a few B's. So that's a B. And then 2, -4 must be a solution because otherwise one would be different. Yeah, this is on the solid line. So that's your first test of this. This is on the solid line that bounds the overlapping shaded region. 2, -4 is also considered a B. These are solutions to the system, whereas A is not. And that's probably a good thing that I wrote. It says, how can you verify an ordered pair as a solution? It's not just plugging numbers in. It's also checking on graphs, which you have an option to do. So it's a good thing I mentioned both. All right, guys, we're going to go and we're going to get started with the problem set, numbers 3 through 48. A lot of graphing will be had, but of course they introduce you early on to probably items of substitution and checking that things are solutions, which is a nice way of drilling and killing. Because this is going to be a lot like the previous section, only now that we have 2 things to consider. It's good that we introduced ourselves to it first before we move forward. Okay, next it says 3 through 6. Tell whether the ordered pair is a solution to the system of linear inequalities. If you were just with me on number 2 in the vocabulary and core concept check, then this should look pretty close to what we were doing. So I'll get these all set and ready to go right now. So whoa, that's for later. Sorry about that. So -4, I had the wrong pen out. -4, 3, -3, -1. I'm just getting them all set right now. -2, 5, and 1, 1. Without need of equation or inequalities, expressed algebraic versions of these things in the system, we can basically see if they belong in the overlapping shaded region. -4, 3, 1, 2, 3, although on the solid line, does not count because it's not bounding by the overlapping shaded region. So, not a solution. -3, -1 is indeed a solution. It's inside the overlapping shaded region. -2, 5, definitely not, and definitely not. Nothing about it is. And 1, 1, is that it? Whether there's solutions? And 1, 1 also is not. Okay. Now, that was weird. Oh, I should have just moved forward. Boom, 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 boom. 3, 4, 5, 6. So only one of them was. Now, I want to also make mention that just because you can't see things within a window range doesn't mean that it could or couldn't be. Now, you'd have to know how these lines actually work, but what if I asked like -50, comma, -1 billion? -50 is way out here, -1 billion is way down there though, and I believe that it's within the overlapping shaded region, so that would work. So things like that. All right, more no's than yeses. I didn't actually expect that. And for very obviously not solutions as well. It was kind of an interesting set, but we'll keep moving forward. Okay, number 7. Rather, number 7 through 10 tell whether they are solutions. So this is kind of back to, now we get to do a substitution on these ones. So -5, 2 into the system that is y is less than 4 and y is greater than x plus 3. So you'll be doing a substitution of both of them on here. We got to check. There is no x on the first one, but 2 goes in for y. 2 is less than 4 is a good old fat check. So far, so good. And then 2 is greater than -5 plus 3 is the next test. 2 is greater than -2. That's also a check right there. So again, it needs to make a true statement, and it needs to make it for both. Because both are true statements, yes, this is a solution to the system. Like I said, I'm not going to be doing my own double checks personally like these ones, except, 0, 0 is actually a good one to do, but there are 4 different regions to look at. If you look at this last graph here, here's like region A, B, C, and D. A, B, C, and D, and only one of them qualify. So even if I checked and saw 0, 0 was a solution and it wasn't, it doesn't mean that I know what other kind of region I have to shade it in, so that's probably not the best test to do. So like I stated, unless they're asking me to check on one or to come up with my own, I'm likely not going to do my own checks for them. Okay, 1, -1. Again, the first one only has a y, so we substitute -1 for there. -1 is greater than -2, a smaller negative number, and -1 in comparison to 1 minus 5. Yeah, -1's greater than -4. Also checking out. So yes, once again, solutions. So all the ones that weren't solutions in 3 through 6 are now being made up for right here. Now we're getting a bunch of solutions. We'll see if we can get 3 out of the 4 become solutions. I'll feel better about the first ones being so off. All right, 0, 0. Versus 2 linear inequalities that feature both y's and x's. 0, 0 is always the easiest kind to do. I'm literally going to not show any work on them other than write the statement, because plugging in 0 kind of wipes out everything except for what's added. So 0 is less than or equal to 7 is true. 0 is greater than or equal to 3 is not true. It takes 1 for this to be a no. It just takes 1. Doesn't matter that the other one was true. And then number 10, kind of hoping the first one to be false to make the point that once I find the first one to be false, then I can move forward. Or, then I can say no and just be done with it. So let's check this one out. Okay, both less than or equal to's. That does mean if they're equal to, by the way, because that might be part of this test. But if they're also equal to, then, it's good. So -3 is less than or equal to, that's the opposite of 4 plus 1. Oh, case in point right here. -3 is less than or equal to -3 is a true statement. It's equal to, this would be basically on the solid line. But is it in the overlapping shaded region? Or is it bounding the overlapping shaded region? That's a question as to whether it fits within this one. So -3 is less than or equal to 5 times 4 minus 2. Oh, yeah. That's definitely in this shaded region. 20 minus 2, or 18. So, yep, definitely. This is a big fat yes. This is, once again, one of those examples where we are on an overlapping shaded or on a solid line bounding the overlapping shaded region. It's kind of one of those. Only very deep into the overlapping shaded region. Okay. Numbers 11 through 20 graph the system of linear inequalities. This is where I think we make the most money out of our experience, not actual money, but just you get wealthy with experience on these kinds of questions because of what you're doing most out of them. This is where we have to use graph paper and such as well. So greater than or equal to -3 and greater than -3, greater than or equal to 5x. So we did all of our graphing of these kinds in the last section. So I'm going to be pretty fast with these as an overall. We first graph y equals -3, which is a horizontal line like so. We determine whether it's solid or dashed line by the fact that it's not equal to, it will be dashed. And we shade above this line. We shade above this line because we are greater than. So greater than's above. Now keep in mind, we are going to determine the overlapping shaded region with this and another line itself. Sorry about that, having a darker spot there. It's just going to be what it is. Y is greater than or equal to 5x. Let's use, I guess, green. Y is greater than or equal to 5x. So I have to set up some of my color sets here. Can't see it on screen. Okay, so I have a y-intercept of 0 and a slope of 5. Now, greater than or equal to, I made mention of this back in the day, back in the previous section, where if I dropped a kid on the slide, would he fall on the slide or not, depending on what side of the slide I'm on? Above the slide is, because this is above the line, so above the slide is right here. If I drop the kid, whee, he falls on the slide right there. So there's an example of that. Therefore, the greater than side is right here, okay? It's harder when it's steeper to determine which side represents greater than, but it represents it right here. Now, the part that's kind of tougher to picture is what's the overlapping shaded region. I mean, I hope you can picture it, but from my drawing here, for my money's worth, I'm going to emphasize that with a little bit of, I guess a little bit of red. So this is my overlapping shaded region right there in red. So when it says graph it, ultimately, this is the part that matters. Whether I would delete these other portions or not, oh, see, look at what that does. But whether I would delete these other portions or not is kind of an up to you thing. I'm going to bring it back. I'm going to undo this. But this is the part that matters, okay? That's the part that ultimately matters. So let's undo, bring it back. So there's our graph, our set. Okay, number 12. Now, they didn't mention something like provide an ordered pair that's a solution and one that's not a solution. Maybe that's something that they do later, but that's not here. So number 12, we have y is less than -1 and x is greater than 4. Now, each of these are very simplistic. People tend to, students tend to coin these ones as like harder problems because there's less. Like, I want my slope-intercept form. Well, the first one's kind of in slope-intercept form if you know what you're doing on slope-intercept form. It's y equals 0x minus 1 as a boundary line, but less than means dashed, and less than means shading underneath. The x, on the other hand, get my blue on. The x, on the other hand, we don't shade above versus below, we shade left of versus right of. So, because an x equals equation is a vertical line. So x equals 4 as a boundary line. What I use green. X equals 4 as a boundary line looks like this right here, vertical line. Greater than, without being equal to, means a dashed line, and the greater than means we shade to the right of it. There's no shading above a one of these things like I stated before, and it is comparing x's, just like we did on number lines back in the day, we shade to the right of it. So the overlapping shaded region is the one in this bottom right, I can't call it a quadrant, but the region right here, that bottom right area. So this is that set. I got to find a better way to do that. Maybe like that. Boom, 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 boom. Okay. That's the one we care about. So for yourself, kind of, shade lightly with a pencil here and here, and then darken that area there, something like that. I got to find a better way to do it. My only problem is I'm using a stylus that's really my tips wear thin on my styluses. I don't really know what to call them. It's probably styluses. But my tips wear thin if I do too much rubbing around on them, especially when I feel like I'm putting pressure on it unnecessarily. Oh, okay, this one's interesting. So we're not quite getting just two slope-intercept form ones yet, as you can tell. They want to play around with vertical and horizontal lines. In this case, horizontal lines. Y is less than -2. Here's my y equals. Here's my less than when I do that. And give me a second. And that, shading underneath. Now, shading above, or excuse me, the other inequality will be shaded above. So y is greater than 2 looks like this guy, also dashed. Most of these are dashed. And we shade above here. Now, there is no overlapping shaded region. Excuse me. So, as you've kind of seen, I darken the overlapping shaded region that's on these. You can probably do that by default and just say, hey, these are my solutions. And it's an infinite number, right? And I could call out a solution if I wanted to. 10 comma negative 3 is a solution to it. But here, we have to identify what solutions exist, if any. In this case, there aren't any because there's no overlapping shaded region. There's no y value that is both greater than 2 and less than negative 2 at the same time. This is a no solution case, and it must be identified as such. This is a no solution case. Number 14. This might feel the same. Now they're slope-intercept form together, though. So y is less than x minus 1. Let's first graph this x minus 1. That's a slope of 1 and a y-intercept of negative 1. So all these points here. We're going to draw on this line. And we will do a dashed line. We'll do a dashed line, and we will shade underneath the line. So dashed and, excuse me, line with arrows. Dashed. And some underneath shading. Less than. Okay. Y is greater than or equal to x plus 1. Y-intercept of 1 and a slope of 1. So it's parallel to it, which parallel does not guarantee there's no solution. It's all about the shading. However, because we're shading above this line, solid or not, because we're shading above this line, there is no overlapping shaded region or intersections of these lines here. So with this one, we are shading above this solid line. It is solid, we shade above. That doesn't mean there's a solution because there's no overlapping shaded region. Sorry, everything I'm doing is logistically slow. I have to get a lot of things taken care of just to get my shading on. So my words are ahead of my art. All right, overlapping shaded region, none. Solutions, none. I no solution. Get at least 2 examples of those. Again, it's possible for parallel lines to have solutions. They just need an overlapping shaded region. What if we were under the green and above the blue? Then it would be all within here. And those are kind of some of my favorite ones. The ones that are like, hey, they're inside here. We'll see if we get any of those later. Number 15. We have a horizontal boundary line to begin with, and then something that's not quite in slope-intercept form. I think I want to do a little bit of a rewrite of that. So it says currently y minus 1 is less than 3x. You could argue this is point slope form right now because it's 3 times x minus 0. Boom, boom, boom. But I'm not going to stick to that. I'm going to get y by itself there. So rewrite that one down there as y is less than 3x plus 1, okay? So the first one, I mean, this one isn't unique in any sort of way other than we had to rewrite that y bit. But this one here, greater than or equal to negative 5, is a solid line on, a solid horizontal line on negative 5 for y, and then shaded above. Oh, I have a crayon. Hold on, I have different pen options. I wonder if any of these, I don't know. I have to look at those later. I just saw there's something called a shape. I have something called a shape recognition pen. I'm very curious to see how that works, and I probably want to try that right now because otherwise I'll forget about it. So I want to see what it does. Obviously, if I start to draw something, it must make a shape, but that sounds really cool. Let me actually just experiment. Shape recognition pen. Let's see. Triangle. Hey! I'm going to use this in the future. Pentagon. Oh my gosh! I'm going to start using that. Hold on. Oh. Okay. Anyway. That's interesting. Okay, there's nothing to do with the problem. All right, y is less than 3x plus 1. Let's get out of the shape recognition pen option there. 1 is my y-intercept. 3 is my slope. How do you count to 3? 1, 2, 3. Boom. Okay. Dashed line. We'll get there. And then shading below because it's less than. So dashed. All right, let's shade below this guy. Now, one thing I want to state. Let me sip water while I'm doing it. One thing I want to state is sometimes, you know, especially because you're not color coding it, probably. Sometimes students have trouble with the second shading thing, like meaning you draw the line and we start shading. You start doing like, I'll bring this back, but you start only shading just this area right here. Like you start attending to that line. This line should have nothing to do with this inequality. It only has to do with the system. That's why we need to shade it specifically where it goes there with respect to the system. So you just shade underneath, you just shade underneath the green line. Doesn't matter that part of it's inside the blue area. Anyway, the overlapping shaded region, we haven't seen one of these in a while. The overlapping shaded region is all this right here. The intersection of the half shades, right? Number 16. I need more water, man. Excuse me. Okay, 16 has a standard form inequality, and I intend to graph this one out of standard form to remind you of what it looks like. Meanwhile, we have one in slope-intercept form. I expected a few more of these ones, but we still have this one and 4 more to go, so I'm sure that's plenty. So we got this set here. I need to bring these a little closer. Okay. Because otherwise this won't really fit. There we go. So in the first one, let's first graph x plus y equals 4. That means they each have an x-intercept of 4 and a y-intercept of 4, right? So they hit here and here, and you'd use your ruler to draw a line. Now, keep in mind with this line that it must be, let's figure this out. It must end up being a dashed line because it says greater than 4, not greater than or equal to 4. So we will dash it up. The other thing is because it's standard form, you'd have to be very cautious and careful. There are reasons to know whether this is going to be a one way versus the other. Greater than doesn't necessarily mean shading above when in standard form because it's not y is greater than. It says x plus y is greater than. So your best thing to do here is test a point such as 0, 0. When I plug in 0, 0, is 0 greater than 4? No. Therefore, on the side of 0, 0, I will not shade. I will shade on this side of it, which happens to be above. But I would be cautious of assuming that you shade above just because it says greater than in a situation where y is not alone. So unless you're rewriting it in slope-intercept form, which you absolutely could, it's just this is my first problem I got to do in standard form like this. Unless you're doing that, I would caution against not testing a point. All right, y equals or greater than or equal to 3 halves x minus 9. So up 3 over 2. Don't mind if I do. By the way, these ones don't need any sort of semblance of that point of intersection really mattering for us. What I mean by that is it's okay that these two intersect at some probably random fraction set for x and y. This is not at the 0.5, negative 1. It's 5 point something and negative 1 point something. It's kind of a strange one at that, right? But it doesn't really matter this time. Our solution set, we're not really calculating. We kind of just draw. Right? We are artistically determining what the solution set is. I'm going to shade above this one. This is a y by itself kind of situation. So when it says greater than, yes, I do shade above the green line. Here's all that's green that doesn't matter for our solution set that I'm doing, and everything that's with the blue does matter. The overlapping shaded region, of course, right? So all that matters for us is this area right there, including points on the solid portion of the line. I don't want to forget that aspect of it. So all those are solutions. Number 17. A lot of pen changing here. So number 17, I have x plus y is greater than 1. I can also do that one out of standard form. negative x minus y is less than negative 3. I can also do this out of standard form. So I'm going to do these out of standard form as often as I can. I kind of caution on the x plus y equals 1 only because they are so close together. They're so close together that your line could technically become a little inaccurate. The farther away your points are, the better off you are at making a line that goes through them. But if I have an x-intercept and y-intercept of 1 like this, it could lead to some significant inaccuracies in your line if you're not careful on what your slope's actually looking like. Because clearly the slope's supposed to be negative 1, right? But I could do something where I could maybe draw something like this that's like, oh yeah, look, it goes through the things. But maybe it's not necessarily all that close to an accurate portrayal of the line that it's going through, because that's not a slope of negative 1 anymore. It's not really working out that way. If I want it to be a slope of negative 1, I got to really make sure that I'm kind of hitting those diagonals over and over like that. So this is one to be careful of when you're doing standard form. You might attend less to precision when on it like that. So I believe this is going to be my slope of negative 1, like that. Now I'm not done, clearly. Greater than this means dashed. Now testing 0, 0, I get 0 is greater than 1, not a true statement, so I will shade above. At this point, you're saying, well, Mr. Robinson, we are 2 for 2 in greater than being shaded above in these things. So I must therefore make a conjecture that greater than will always mean shading above. Not so fast, my ignorant pupil. Let's look at the next one. The next one, the intercepts are both 3. If you divide negative 1 or negative 3 by negative 1, you get 3, and negative 3 by negative 1, you get 3. So these intercepts are 3 for both y and x. Boom and boom. We are doing the same thing, and this is where, it'll be a little more accurate in my book, at least, when I do my precision is going to be a little bit easier to work with. Not significantly so, but maybe more significantly better than the negative ones. Just still be careful of your slope. Your slope is still negative 1 even on this one. So they are parallel lines, and this is a dashed line. Now, there will be a solution set here. This is inside that shaded region, whether I shade above or below it. Which one will I do? You see less than, you might think shade below. Let's take a look. Try 0, 0. Is 0 less than negative 3? No. So we shade above it. We don't shade below. Mr. Robinson, it says less than. Well, that's what I was telling you. Unless y gets by itself. And that's the idea. If I got y by itself on this thing, I'd have to eventually divide both sides by negative 1 in the equation, because y is negative. And dividing by a negative would flip the inequality. So just to give you a version of what these rewrites of these ones here are, this second inequality can be rewritten as negative y is less than positive x minus 3. Divide everything by negative 1. Y is greater than negative x plus 3. And that's exactly what this is doing. Y-intercept of 3, slope of negative 1, not equal to, so it's dashed and shading above. You can see the inequality flips when I divide it by the negative. Now, just because the lines are parallel doesn't mean there's no solution. In fact, anything above the green is also technically above the blue, but anything above the green is in the solution set. Therefore, really, it's this inequality technically means nothing with regard to things in the system. As long as it satisfies this one, it will satisfy that one. Know what I'm saying? So there's number 17. Number 18, despite having this initial problem in standard form, the x-intercept would become a fraction. So instead, I am going to rewrite it in slope-intercept form. Same with this one here, despite it probably being a little bit point slope formish. It's not our favorite appearance. So let's do a rewrite of both of these. And let's do it below. Let's do a rewrite of both of these here. And I will have the first one as y is less than or equal to negative 2x plus 5. And this one, y is greater than or equal to negative 2x minus 2. Off the bat, I'm seeing that they have the same slope, so I'm curious as to whether these are no solution cases or not. Knowing what I know about these, not necessarily. These might be my favorite kind, actually. So here, the funky looking ones, plus 5 and a slope of negative 2. I did not count down 2 right there. There we go. Okay. This line is solid. It is, man. It's a solid line, bruh. Like that. And we will shade below it, less than. I'm going to try a different kind of shading this time. I'm going to have it a little, just moderately thick, but kind of try and do this right here. Hope that's okay. That actually probably wore out my tip more, so maybe I'm not going to do it as often. I'll do it still on this problem because I started it, and I don't want to waste it now. So negative 2x minus 2 is down here. You're like, I don't like this one as much. Yeah, me neither. I just wanted to give it a shot and see what it looks like. This is ideally what you'd be doing, although a lot better looking in pencil. Because you can't do that kind of thicker thing that I'm doing. This one's also a solid line, but this time we shade above. So shading below one and above the other, despite the fact that the lines are parallel, again, does not guarantee you have no solution, right? This is an instance of that. So shading above this one would look like that right there. So what's kind of the cool thing about this one is the tweener set being the actual solution set. That's not standing out quite as much here. Let's see. Let's do kind of this red. I'll just do that. So this is the solution set here. So these are the ones I like that just go, wee, anything within here. 0, 0 is a part of the solution set there. And yeah, that's the overlapping shaded region of that one. Okay. Numbers 19 and 20 have 3 inequalities. These ones would kind of look more like some of those word problems, at least the word problem that we saw in the lecture portion. So x is less than 4, yet y is greater than 1, yet y is greater than or equal to negative x plus 1. So they do have a pretty nice progression system when it comes to what we're doing with graphs and how we learn off of them. I applaud them for that. Nicely set problems, folks, of Big Ideas Math. Well done. So I need 3 different colors this time. I don't need them, but I do them. X is less than 4. 4 is over here. Less than means dashed and to the left of for x. So I'll go back to what I was using before. Right here. Okay. There's our first one. Y is greater than 1 is a horizontal line, a green one at that. Is yours green? It is also dashed, being greater than, and we will shade above. A y is greater than, we will be shading above that there 1. So here's our overlapping shaded region in the top left, if you will. But we are still not done. Not to be outdone is y is greater than or equal to negative x plus 1. So final color, I guess I'll just use purple. Y is greater than or equal to negative x plus 1, a y-intercept of 1, a slope of negative 1, like so, and we will shade above this one. So ultimately, we'll have an overlapping shaded region among 3 inequalities in the system. I guess it's going to represent a triangle here. We'll see in a moment. Like I said, some of our word problems will take form like this. Now, this is a solid line, and we are shading above said solid line. Maybe these colors blend a little too close together, green, blue, and purple, but I do what I do. So shading above this one here. They look different. So what's the overlapping shaded region? I'll make that in a nice red. It's this right here on the solid line that bounds it and inside of that region right there. It's tougher on my end. I'm sure with pencil it'd be easier on your end, but that's the overlapping shaded region of those 3. Now it's not anything on the dashed lines here, but on the solid line, yes. Last one, number 20. X plus y is less than or equal to 10. That's a good one as far as standard form goes because these y and x intercepts are 10. Those are pretty far away. X minus y is greater than or equal to 2. It's pretty close. And y is greater than 2. Okay. So with this one, less than or equal to 10, our x and y intercepts are 10. So this, like I stated, I'll be pretty precise on, all told. Given that going through 2 points that are farther away, that'll adhere to my slope a lot more significantly so, right? I don't need to do much more fixing on that other than the little snap thing that had at the end. Now, it is a solid line. Less than is not necessarily below. Compare a point like 0, 0. Is 0 less than or equal to 10? Yes. Okay, we will shade below on this one. So, shading below is this fat amount of content right here. See, that's the toughest part for me, going down the line like that. Is this all that's a solution? Not yet, not necessarily. I don't know what the other ones look like and how we compare just yet, so we'll see. All right, next one is x minus y is greater than or equal to 2. Now, x-intercept is positive 2, but y-intercept is negative 2 when you divide by negative 1 there. So we're going to go this way. It's also a solid line, but it's a green one. And I got to extend it out further. And let's test a point such as 0, 0. 0 is greater than or equal to 2 is a false statement, so I won't shade on the side of 0, 0. I will be shading below. This is a case where greater than is a little misleading because y was not yet by itself. Of course, in getting y by itself, that would mean an inequality flip would be had because we would have divided by negative 1. So we do shade below this one. You can now start to see part of the overlapping shaded region take hold. But not until we get our final one will we know exactly what it looks like. Y is greater than 2 is the last one. That is a horizontal line, like so. It is a dashed line, being only greater than, and we will shade above. Now again, I don't know what's required out of you and what's taught of you, but if you sketch all three overlapping shade or all three shaded regions lightly, you can then darken that last one, which includes this boundary line up to here, this boundary line up to here, does not include the dashed line there, and it's this triangle within there. That's the overlapping shaded region of those three. Very small set, but still an infinite number of solutions. That doesn't change. Okay, numbers 21 to 26, they ask us to write a system of linear inequalities represented by the graph. So these are mostly going to be slope-intercept forms of things, unless they have vertical lines, but slope-intercept forms of things that we can determine those. It's all about shading above versus below, whether it includes them or does not. So I'm going to keep them probably on that side. I'll copy and paste them. I might have to do some slopes. Not yet, but kind of one at a time, right? So there's the problem. So our system will have two inequalities. The first one we'll do is this horizontal line right here. That's a y equals equation. That is a y equals 3, if you will. However, the shading is below and it doesn't include the line. So not equals. It'll never be equals. It might be or equal to. But y is less than 3 is the first one. Next one is a vertical line. That's an x equals equation. That's an x equals negative 1. Not truly equals, right? Solid line means it can be equal to, but to the right of is greater than. And remember, the overlapping shaded region is all that is shown. They don't show the other parts that say, well, it would have been this for x and it would have been this for y. Whoops, I was trying to use a different color. And it would have been this for y, and there's the overlapping. No, they're just showing the overlapping. So just keep that in mind when it comes to it. What is to the right of this line yet below that line are both of these. So that's number 21. Number 22, we have two vertical lines, and we're in between our sets here. Now, writing a system means we're not going to do it as a compound inequality, but I could. I'm going to show that afterward. X, this is 2, this is x equals 2, this is x equals 4. We're to the right of the 2 and to the left of the 4. So x is to the right of the 2, x is to the left of the 4, doesn't include either of them. So that ends up being, or they're dashed lines, so it's like that. I'm curious if I'm allowed to write it like this as well. It's no longer a system, but it's compound. That's kind of another version that I'm thinking of. Hey, it's between 2 and 4, you idiot. Probably not going to write it like that, but I'm still want to show that one off and say, hey, remember how compound inequalities work? Okay, number 23, back to form, slope-intercept form. We have. So on number 23, this is where I can make better use of having this copied and pasted over because I want to talk slope and point at them. So the first one I want to mention, I guess, is this one right here. We got a y-intercept of negative 2. We got a slope of, find another point that's defined right here, like up 2 over 3. 2/3. So 2/3 x minus 2 compares to said y. Now, it's not equal to. It's a solid line. It can be equal to, and we're shading above it. You can tell by that. So y is greater than or equal to 2/3 x minus 2 is here. The next one has a y-intercept of 2, positive 2, like so. The slope goes down 3, right 1. So that's a negative 3 slope. So negative 3x plus 2 compares to said y right here. This is also a solid line, and it's also shaded above, right? In this case, shaded above. Boy on slide can fall on slide. So it's also greater than or equal to. This is your system for which we can write them. So all these guys, I'm going to write them in slope-intercept form, assuming they're not vertical lines. But I'll write them in slope-intercept form, not standard form or something like that, or point-slope form. We're just going to use those. Especially because the greater thans or less thans we can shade above or below when y is by itself. That's the easiest way to go about it. Okay, number 24. See, I really think the shade above and below is a lot easier here than doing a point test thing. So hopefully it's really making sense how I'm going about it. Let's start with this first dashed line right here, which means it will not be equal to y-intercept of negative 2 and a slope of 1, up 1 over 1, right? So, and we are above it and strictly above it. Y is greater than 1x minus 2. And the next one is a y-intercept of 1. And I can't see my rise, so I'm going to go down 5 and left 1. That also means we go up 5 and right 1, right? It's still a slope of 5. So, slope of 5, y-intercept of 1, it's equal to and also below, right? A boy right here drops down, does not fall on the slide. Ah! Like that. Wee! But is below it, okay? Below the line. So y is less than or equal to 5x plus 1. Two more on this set. Now, number 25 says write a system of linear inequalities. Now, as you can tell, there's no overlapping shaded region. This is a case of no solution. That's not that we write no solution. We still have to write what these two systems are that represent no solution here. So that they are parallel. We're going to come up with their slopes and such. But because because nothing's overlapping, we're going to assume very heartedly that we are above this line yet below this line. Okay, that's the idea to really make this thing what it is. So that first one in blue that I did, that is a y-intercept of negative 1, and it looks like a slope of negative 2. Down 2, right 1. You can tell up 2, left 1 right there. So this is y is greater than negative 2x minus 1, excuse me. Negative 2x minus 1, but it's greater than to shade above, so it doesn't overlap it. And this is a less than shading below it, and it's a slope of negative 2 as well, but that y-intercept is 3. So that's what will give you those graphs, which also are no solution. That's what that means. Now, number 26 is also kind of a weird example of how the overlapping shaded region works. We saw one of these when we graphed them ourselves together. But when you have something like this, where, again, the lines are parallel, but we do have solutions, we're greater than that one line, but we also then therefore must be greater than the other line. You might say, well, Mr. Robinson, why doesn't it show the shaded region of it? Well, because they're only showing the overlapping parts. So if we are above this line, yet also above this line, what's considered to be the overlapping shaded region is just what you see, what they have right there. And that includes this boundary line. Those will be solutions, but they are parallel. So let's start with that top one. It is a greater than or equal to, because it's also solid. Sorry about the weird curly brace. Y-intercept of 0. And we go up 1 over 1, 2, 3. So 1/3 x, like that. The next one is also greater than or equal to, and it also has a 1/3 slope, but a y-intercept here of negative 2, like that. So this is both of them. To be greater than this one is to always be greater than that one. So really, this one means nothing to us. But still part of the system, so we include it. All right, that's 21 to 26. Let's go to the next page. Past the halfway mark because we go to number 48. Numbers 27 and 28 on error analysis. Describe and correct the error in graphing the system of linear inequalities. So let's see what they have to make mistakes on here. Less than or equal to x minus 1. Ooh, they shaded above it. And greater than or equal to x plus 3. They shaded below it. So they have their mistakes are in their shading. They shaded above a line they should have shaded below. and they shaded below a line they should have shaded above. Now, this is me saving myself a little bit. I'm not going to redo it. I will state that if we do, because y is less than or equal to x minus 1, that's this line here. I could tell by the y-intercept. The slopes are the same, so we should have shaded below because the less than or equal to. This one says greater than or equal to x plus 3, we should have shaded above. Because that shading would be there, there is no overlapping shaded region. So the only thing I'm going to state on this is, with the new shading, there is no solution. So keep that in mind, because there's no overlapping shaded region, there's now no solution to this. Before, there were solutions anywhere within the overlapping shaded region, including 0, 0. Actually, I'll leave them there. Including 0, 0. Okay, I can't apparently undo my marking. There it is. But now there's no solution now that our shading kind of looks like that instead. Remember, very light shading, nothing overlapped. Number 28. Let's see how they wronged us here. Oops. All right, y is less than or equal to 3x plus 4 actually looks legit. That slope of 3, y-intercept of 4, solid line, and shaded underneath is all good. Y is greater than 1/2 x plus 2. That's a 2 right there, slope of 1/2, and it's dashed, but they shaded below. So they should have shaded above the second one, which does kind of completely change the outlook of the overlapping shaded region, which is the part that I'll fix. So the first inequality is graphed correctly, including shading, because it's underneath. But the second inequality, so these are all about which way they shade. Should have been shaded above, which completely alters the overlapping shaded region. See, previously, and I'm going to keep the graph as it is right there, but previously we shaded below this one, and then they also shaded below this one. That's why the overlapping shaded region is as you see it in this area. But now we're going to shade above this one, so the overlapping shaded region now goes in this one right here, in that top right. So instead of having what you see there, what we would now change it to, basically if we only had one of them, is just this guy right here. This is below that solid line, yet above the dashed line. This would be the fix of that graph as a whole. So I'll just leave that one right there like that. Okay, number 29. Modeling with mathematics. My favorite kinds of word problems, systems of inequalities. You can spend at most $21 on fruit. Blueberries cost $4 per pound and strawberries cost $3 per pound. You need at least 3 pounds of fruit to make muffins. Write and graph a system. So with these ones, you are going to want to use x and y when it comes to graphing things. So let's let x represent this, y represent that. These are not our system yet. These are just defining variables. So let's let x represent pounds, number of pounds of blueberries, pounds of blubs, and y is pounds of straws. So many straws, yo. I'm dying for some straws here. It's more straws than you can shake a stick at. All right, so as far as our system goes, we got a few things going on here. You can spend at most $21 on fruit, and blueberries cost $4 per pound. So that's a 4x plus 3y at most less than or equal to 21. You need at least 3 pounds of fruit to make muffins. Fruits, oh, that's both of them. So your combination of blueberries and straws needs to be at least 3 pounds. Now, 2 other things that I could put in play, and I probably should. You know, I'm going to extend this a little bit. When we did section 5-6, these also applied. We just didn't really write them. We just said stay within there, and I'm going to do the same thing here. We got to kind of stay in the first quadrant. So as much as we need to stay above these together as a whole, this also needs to stay above 0. This also needs to stay above 0. I feel like those ones will be a little more so implied. Like we'll just stay in the first quadrant and be good on that. And I get it. That will just be implied there. Oh, that was an old thing that we had. Let's copy and paste one of these graphs. Here's what I need though, guys. I just need the first quadrant. So I'm going to try and give me 1 second. I'm going to snip out just this one part so it doesn't get as in the way. Okay, so I think, because I think the next one's also a word problem there. So let's just get this portion, this quadrant here. And we're going to do some graphing based off just this first quadrant alone to make some things happen. So the greater than 0 things, I think in the future I'm just going to imply, unless it's a part of it needs to be positive, it can't even be 0, then we'll restrict it. But because they didn't state anything there, we'll just say first quadrant only, we're good. Therefore, even our graphs won't have arrows, but let's do a little bit more of a rewrite on this first one here, where I have 3y is less than or equal to negative 4x plus 21, and y is less than or equal to negative 4/3 x plus 7. There's our slope-intercept form of that. So for this one, I'm going to go from 7, I'm going to go down 4, right 3. I'll still go down 4, right 3 again. I know that this goes outside of that first quadrant thing I'm talking about, but it's just so I can complete my line, or my line segment rather, right? So my line segment, gonna look a bit like that. Let's thin it out a little bit. It's gonna look a bit like that, and I'm honestly just going to go to here. I'll just cut it off right there. Well, it's a system anyway. That's all right, fine, I'll do that. I really want to marry myself to first quadrant only if I can, and that's an example of that. So that means this x-intercept, I mean, it's not on an integer, just keep that in mind. X plus y is greater than or equal to 3. Oh, by the way, we will be shading below this line. Now, I'm going to try and avoid any overlapping shaded region stuff until I get to the overlapping shaded region part. So we are going to shade, if you test 0, 0, it works out here, so we will be shading below this line. Now, we'll be shading above this line if you test 0, 0, it doesn't work, and this line is having a y-intercept and an x-intercept of 3 each, so they look like that. Boom. These aren't parallel. These aren't parallel, but we're there. And then, again, we're bounding ourselves by these axes, so like this one here and this one here bound this set right there. So we are within this, it's not a trapezoid, but we're within this quadrilateral shaded region here. These represent solutions to how many pounds of strawberries and blueberries we can have, okay? So when I, shade it, we're below the blue, above the green, and, in the first quadrant as a whole. And that's kind of what I want to make there out of it, okay? Whoops. Add a third layer. Oh, well, there it is. Okay, so write and graph. There is part A. I'll probably be able to go faster in the next one now that we understand what that is. Part B. Let's talk solutions. Identify and interpret a solution of the system. Let's come up with one. I'm going to land on, let's say, this guy right here. This guy is inside. And now listen, on the lines would also count. On the lines would also count because they're solid. But right here, this point is 3, 2. That means that to make muffins, to make and afford muffins, I can purchase 3 pounds of blueberries, blubs, and 2 pounds of strawberries. Straubs, yo. So that is my interpretation of that. The thing is, I can afford it. It's within my $21 amount, and it's at least 3 pounds. All right, that's the idea of what we need on that. And we can't have negative of anything there either. Part C, use the graph to determine whether you can buy 4 pounds of blueberries and 1 pound of strawberries. So just using the graph on part C, here's 4, here's 1. Yes, that also works. So part C, totally good. Yes. It's in the overlapping shaded region. We're all good. All right. All right, that's it for that one. Let's go to number 30. More of the same. It's probably the same kinds of questions. We just have a different scenario to make up for that. So this time, like I stated, I will imply the positive thing. I'll imply the first quadrant, unless they state something else on it. You earn $10 per hour working as a manager at a grocery store. You are required to work at the grocery store at least 8 hours per week. You also teach music lessons for $15 per hour. You need to earn at least $120 per week, but you do not want to work more than 20 hours per week. Wow, okay, a lot of things. So I'm going to type this first one out here. Let's let X represent number of hours at the grocery store, and Y represent number of hours doing music lessons. Number of hours managing grocery store. That's way more information than I need, but hours grocery store is all I need. And Y is number of hours. What is it? Teaching music. Number of hours teaching music lessons. These are the things as a whole here, right? Now, we must be positive or, greater than or equal to 0. I think that's a must. But they also say you are required to work at the grocery store at least 8 hours per week. So that is among our restrictions. So X must be greater than or equal to 8. That's already something we need in our set. Now, you do not want to work more than 20 hours per week. Let me do that one next. The combination of hours worked at the store and music here, you do not want to work more than 20 hours. So stay within 20 hours here, even though 8 are at the grocery store. At least 8, I should say. Now, the last one is you need to earn at least $120 per week. So the amount that we work at the grocery store is $10 per hour times the number of hours. And then we make $15 per hour teaching music lessons times the number of hours here. And then we must earn at least $120 per week. So like that would be kind of my setup on those. So I think that's my system. I don't see anything else that we need to pertain to other than y must be greater than or equal to 0, but we'll just stay in the first quadrant. That's fine. So here's our system for part A. And then as much as you're probably thinking to optimize, you're like, oh, that's easy. We can do this, this, and that. Because you're thinking, hey, I make more money teaching music lessons. Yes, but you also need to work 8 hours at the grocery store. You don't want to work more than 120 hours. So, all the stuff that's why we graph it. That's why we graph it. And that's what this big old quadrant is for. So the graph will represent every solution. That's really what I like about these. As much as I never use these in the real world personally, I could for optimization purposes. So remember, we will be in the first quadrant. However, with X as well, greater than or equal to 8, that goes far. You know what? We need to change these scales, guys. Let's change this to 10 and 20. We definitely need it for this one right here. And 10 and 20. Hope that's okay. X is greater than or equal to 8 now looks like this here. Let's see. I should be making the full lines, but I'm kind of pretending like I only have a first quadrant that exists. So making an upward arrow that goes there, but no downward arrow. That's probably shouldn't be doing that. And we'll be graphing to the right of that one. Not yet, but we'll be going to the right of the 8, okay? X plus Y is less than or equal to 20. Now that is, if you think about it, that is x-intercept and y-intercept of 20. So we're going to go from this 20 here down to this 20 here. If you plug in 0, 0, it does work out. It makes a true statement, so we'll be shading underneath this line. So right now we're within this set right here is what we look like. But the third one still needs to apply, and I'll get there in a moment. Let's just make sure that we also know that y must be greater than, I'm also going to bound myself, of course, by this part here. So we're within the triangle so far. Even though I didn't write that one, it's implied. The last one, I can do intercepts. 120 divided by 10 is 12. So for this last one, I do get an x-intercept of 12. Remember, that's actually right here. And then a y-intercept, 120 divided by 15, that's 8, right? I think it's 8. So 8 would go right there. So it's these two, and the greater than or equal to, if you test 0, 0, you get a failure. So therefore, we must be above this line right here. Totally not parallel to that set. But we need to stay within, above this one, below that one, to the right of this one, and of course in the first quadrant. So as a whole, now that I have a few colors there, as a whole, the overlapping shaded region of this will look like this guy right here. And this represents, now all of these, to my knowledge, everything was a or equal to kind of scenario. So boundary lines also, count as solutions here. So I could work completely at the grocery store and do things, things like that. But that's my setup there. Any point on here works. Okay, that's part A. Part B, identify and interpret a solution of the system. Let's pull out something like this one right here. This is 10, 8 based on scale. So I can, with everything involved, I can work, is X grocery store? Yes. I can work 10 hours at the grocery store. Manage it in the grocery store, and teach music lessons for 8 hours. Is this in a week? Yeah, in a week. That will keep me above 8 hours at the grocery store. That'll keep me under 20 hours of work, and that'll get me more than $120, right? That's what the shaded region's doing. Like I said, to me, these are kind of fun in seeing that. Part C, use the graph to determine whether you can work 8 hours at the grocery store and teach 1 hour of music lessons. Okay, that's right here. No, that's not even right there. That's 2 hours of music lessons. This is right here is like that. Although it's on the solid line right here, it's not in the overlapping shaded region. So no, you cannot. Part C is a no. I don't want to explain it. I have the point there to tell me exactly that. Basically, what's the part that it fails? It fails the $120 made. You succeed in the keeping under 20 hours, yet having 8 hours at the grocery store. You don't make $120. If you want to double check that, 10 times 8, $80 plus 1 hour is just $15. That's $95 made. That's the one that it fails. And that's kind of why that one works there. So again, the graph is a really nice representation of what you can do. It's not a need. There's an infinite number of solutions. But I wanted to spend some time on that just to talk about that. Okay, number 31. How long have we gone? Well over an hour. You are fishing for surf perch and rockfish, which are species of bottom fish. Gaming laws allow you to catch no more than 15 surf perch per day. I don't know what surf perch. Well, it's pictured right there. And no more than 10 rockfish per day, and no more than 20 total bottom fish per day. Writing graph of system linear inequalities. Once again, the implied is you can't catch negative amounts, so just kind of understand that. We'll stay within the first quadrant. So, let's define variables first here. So let's let x equal number of surf perch and y equal number of rockfish caught per day. Hold on, I'm trying to increase my font. All right, let x equal number of surf perch. I mean caught, but just quantity. So we know it's not weight, it's not dollars. Number of rockfish. Okay, and you do want to use x and y for the sake of your graphs. So part A. Part A will have species of gaming laws. No more than 15 surf perch. You can catch 15, but that's it. Now keep in mind, you can't catch less than 0. That's implied, okay? No more than 10 rockfish. And no more than 20 total. When you combine these, it still must stay under 20. I think that's the only 3. All right. So this one as well, I think we need to work off that scale of 20s because of the sum of those things and the intercepts that we'll have. So I'm going to change these ones here to 10 and 20 and 10 and 20. Once again, we'll stay in the first quadrant only. So let's just use black for all these lines this time. Let's see if we can get away with that. X is less than or equal to 15. Now 15 is right halfway smack dab between 10 and 20. Staying in the first quadrant will look like that right here. Look, it goes up forever, but at some point we're going to limit ourselves in what we do up that way, so we're good. Y is less than or equal to 10. Would look like this right here. Now, less than or equal to 15 is to the left of this. Less than or equal to 10 is less than under that. X plus y is less than or equal to 20. From 20 to 20, right? Those are our intercepts, and it's under that. But then we get to stay within the first quadrant here. So this, our graph part, all these are great, but it's not the triangle. We're not staying within the triangle. It's not like, oh, to compete, you must catch at least 20 rockfish. No, it's actually the other way. You no more than 20 bottom fish as a whole. So this one here is going to be this area like that. You can catch 0 if you want. You can't catch negative. That's why we're not using those ones. Well, I think I used the wrong kind of tool. This thing's going to shrink on me a little bit afterward. It's going to change. Hold on. Watch when I let go. It's going to do... Oh, barely changed. Okay, good. All right. That's part A. Part B, use the graph to determine whether you can catch 11 surf perch and 9 rockfish in one day. 11 surf perch, 9 rockfish. I believe that's right on the thing right here. If it's on a solid line that bounds the overlapping shaded region, the answer is yes. It says use the graph. I could use the inequalities as well. 11 is less than or equal to 15, 9 is less than or equal to 10, and 11 plus 9, which is 20. It's not less than 20, but it is equal to 20. B is yes. Big old fat, That is nowhere near. There we go. Okay. Those 3 problems were my favorite ones that I did. Number 32, reasoning. Let's see if they can have more fun ones somewhere. Describe the intersection of the half planes of the system shown. Oh, I'm not a half plane fiend. Okay, this one's kind of interesting. So notice that they are the same boundary line. They're the same boundary line. They're both equal to, which means points on the line count. One is above, one is below. It says describe them. Here's the thing, because, and I want to go without an official graph here, because I couldn't care less really what the thing looks like in and of itself. But this is, well, let's do it a little more here. Y-intercept of, or x-intercept of 4, y-intercept of -4. Your boundary line looks like this for both of them. They're both solid like that. One of them shades above, one of them shades below. What does it mean when you shade above and below the same line? It means they never overlap. Does that mean no solution? No, because points on the line count. So despite the overlapping shaded region being non-existent, the line, now I was curious if this would pop up, and it isn't this kind of problem. So as far as describing it, the solutions, it says the intersection is all of the points on the line, the boundary line. The boundary line is x minus y equals 4. These are the only ones that actually count. Nothing else above, nothing else below. That's it. Now it's an infinite number of solutions. Just the shaded regions don't really count for anything. How do you be less than or equal to 4 and greater than or equal to 4 for x minus y? When you're equal to 4. And that's what it is. Number 33, mathematical connections. The following points are the vertices of a shaded rectangle. Write a system of linear inequalities represented by the shaded rectangle. All right, let's get graph paper for that one and get it set and figure it out. So on this one here, we have -1, 1. I'm just going to plot the points, but -1, 1. I wonder if it's a diagonal rectangle or just a normal one. Yeah, 6, 1 is just a normal one. 6, -3. And -1, -3. That makes sense. This is a shaded rectangle, if you will. Now, here's the thing. Basically, what we need are what these, it says vertices of a shaded rectangle. We basically need what these lines are here. What is that line? What is that line? These are the boundary lines. And then we are, above this one, to the right of this one, like that kind of thing. But that's our shaded rectangle. What do you mean, Mr. Robinson? It's not shaded. What are you talking about? I don't see any such shading there. We are blowing smoke. Oh, there it is. All right, there's our shaded rectangle on that one. So our system, this is part A. Our system, to me, there's 4 inequalities to mention. Y is less than or equal to 1. Y is greater than or equal to -3. X is less than or equal to 6. X is greater than or equal to -1. Those are my 4 that I'm going to be writing for those ones. Part B asks what? Find the area of the rectangle. Well, 1, 2, this is 7, and this is 4. So area is 7 by 4, which is 28 square units. I don't really have anything to say on that one. Doesn't really have to do with inequalities. So done with that one. Number 34, the following points are the vertices of a shaded triangle. Okay, so this is kind of like this last problem we just did. You know what I should do? Oh, I should try this. I should try that shape tool. What was it? The shape recognition tool? I should try that for this. Now, that doesn't do much for me as a whole, but I want to try it now. So 2, 5, 6, -3. I want to make use of that tool. And -2, -3. That tool's probably been there forever, and I just never even saw it. So hold on, let me try this. Shape recognition pen is what they call it. I'm going to use blue. Let's go from here to here to here and back. Does it recognize I made a sloppy triangle? Oh, it didn't even recognize my triangle. Hold on. It was just so terribly made. Ah, look at that. It's not perfect there. Okay. All right, I'm going to do this again. Okay, let's write a system represented by the shaded triangle. Now, I'm going to first draw the lines because as long as these are to scale, this actually might assist me in, because it's going to be shaded, in finding y-intercepts. I'm going to assume if it looks like it's going on an integer y value that it includes that y value. That way I don't have to use point slope form to come up with my things, okay? That being said, I'm seeing this one looks like it crosses at 1, which is nice. And then let's see if this one looks like it crosses right at a known y-intercept here as I go through that, probably at 9, right? So this one through there and through there. Now, I could also follow some slopes and make sure that it does, but it totally looks like it is, okay? So this first one, when oh, that's the shape recognition pen. I was like, hey, hey, tell me it's a curly brace. Does it make circles? Ah, that's cool. Okay. Oh, that's a good circle. Okay. Let's get her done. First one I'm going to do is the horizontal line. Now, being a shaded region inside of here, which I haven't yet made one. Oh, by the way, this might be isosceles. So I can probably use the isosceles tool for this one. Give me a moment. Let's see. Oh, yeah. Look at that. All right, perfect shading-ish. Okay, so the first one I'm going to use the horizontal line. So that is y is greater than or equal to -3. Now the next ones, again, this one, for example, that is a y-intercept of 1, and we are below it. What is its slope? Because it hits there, that's up 4 over 2 or up 2 over 1. So we are below it, less than or equal to 2x plus 1. And the third one has a y-intercept of 9, and it's isosceles. It must go down 2, right? It looks like down 2 over 1, down 2 over 1 like that. So -2, and we are below that one as well. Y is less than or equal to -2x plus 9. So those are my 3 that I'm getting there. This is part A on the system. Part B, is it just going to ask me for area? Yeah, find the area of the triangle. So a triangle's area is defined by, well, it's 1/2 base times height, but your base needs to be one of your side lengths, and your height must be perpendicular to the base you define. So clearly we want to find this length and then this length right there, okay? So our base goes from -2 to 6. That's a length of 8. Our height goes from -3 to 5. That's also a height of 8. So 1/2 of 8 times 8 will be half of 64, which is 32. So 32 square units is the area of this triangle. Again, nothing to do with inequalities, per se, but part A was, and that's enough. Okay, number 35. Problem solving. You plan to spend less than half of your monthly $2,000 paycheck, less than half of it, on housing and savings. You want to spend at least 10%, at least 10% of your paycheck on savings and at most 30% of it on housing. How much money can you spend on savings and housing? All right, this is, sometimes I have to pause and think about it. Sometimes I write some things out just to keep the conversation going so I can process it, even if I write some wrong things. I've done that before. All right, let's let x equal, what's the first one they said? Housing? How much money? Money spent, well, here they say savings first. Money spent on, what do they say more so? Housing. I'll do savings first. Money spent on savings, and y is money spent on housing. Now this is in dollars on both of them, okay? Okay, let's come up with a system here. How much money can you spend? I mean, it's a system, so I don't know if there's only one answer here or not. So, as far as a system goes, okay, you plan to spend less than half of your monthly $2,000 paycheck. Half of 2,000 is 1,000. So on housing and savings, the amount I spend on housing plus the amount I spend on savings is less than half of 2,000, not even equal to. It's got to be less than 1,000. Okay? This curly brace is too small. I think I need three different inequalities here. I'll do the curly brace after. You want to spend at least 10% of your paycheck on savings. Oh. Shoot. I need to do then. Oh, your paycheck. So savings, X must be at least greater than or equal to 10% of 2,000. I'll clean all this up later anyway. And at most 30% of it on housing. No more than 30% of this on housing. How much money can you spend on savings and housing? So that's kind of what we're looking at here. I might use the graphing calculator for this one if this gets a little weird. So let's clean that up. X plus Y is less than 1,000. X is greater than 10% of 2,000 is 200. And Y is less than or equal to 30% of that is 600. So as far as we can use these, just turn them into thousands. As well, oh, where's my first quadrant one? Hold on. One of these. As far as this goes, boom. just turn these into thousands. So 1,000 and 500 and things like that. That'll be fine. All right, x plus y is less than 1,000. So these are intercepts, x and y intercepts of 1,000. We have to kind of spend under, right? 0, 0. I could spend no money on it, but I can't spend no money on it because I want to spend at least 10% of my paycheck on savings. So 10% is 200. So 200 is right here. X greater than it's to the right of that. And then y is less than 600, less than or equal to 600. So something like this. So my shaded region, and of course, greater than 0 in that case. So my shaded region is looking like this guy. Right in her. Right her. Whatever. It's not going to be perfect, but anything within here works. When it says how much can you spend, I think it's kind of open-ended from here. So I can make a choice of anything within here and I'll be good. Normally they call it thought-provoking or open-ended. It's interesting they say problem-solving because now it's my choice at what I can do. So I could do, for example, and I want to spend like kind of upwards to bigger amounts here. So I could do like $400 here and $500 here, for example. So 400, 500. 400 I think is on savings. So I could spend $400 on savings and $500 on housing and I'd be within my set. So I can spend $400 on savings and $500, and this is in a month. And I'm all good there. The graph tells me all that's good. Okay. Number 36, problem solving on a road trip. So this might be a whole my choice thing again, by the way. On a road trip with a friend, you drive about 70 miles per hour and your friend drives about 60 miles per hour. Let's just say it's 70 and 60. The plan is to drive less than 15 hours and at least 600 miles on each day. Your friend will drive more hours than you. How many hours can you and your friend drive in one day? So let's let X and Y represent number of hours that we drive, number of hours I drive, and Y is number of hours my friend drives. Horse. Okay, so let's come up with this system here. Let's start with, we're going to drive at least, the 70 and 60 miles per hour are going to have to do with how many miles we get total. Let's start with, the plan is to drive less than 15 hours each day. So a combination of my friend's my hours and my friend's hours was less than 15. 14 hours, 59 minutes, good. 14 hours, 59 minutes, 59 seconds, you better stop because you ain't driving 15. So there's part of it. If I drive 70 miles per hour, I'm breaking the law, man. Here I go. My friend is all cautious. And 60 miles per hour here, this is how many miles that we travel in total. 70 miles per hour, it's rate times time. Rate times time, rate times time. It's distance plus distance. Now, we have to get at least 600 miles each day. So we have to get at least 600 miles each day. And then you're thinking like, just you drive the whole time, right? Well, your friend will drive more hours than you. Your friend will drive more hours than you. Why? I don't know. Bragging rights? I don't know. Sleep schedule? Who knows? Who knows what it is? Just different things, right? So that's also consideration. Less chance that you'll break the law. So assuming 65 miles per hour, I think, which is actually a bad assumption. There are places where 70 miles per hour is very much within the limit. So there's our system. And in terms of graphing, look, I'm going to be a little less particular. Well, I'll still use the thing, but just understand this x-intercept is going to be a little off kilter. So we'll probably rewrite this second one in slope-intercept form, and the scale is going to have to be a little bit larger here, right? So we can go up to 20. That's fine. 20 and 10, 20 and 10. Or better yet, let's do this. That's 10, right? That's fine. We'll do this. Now this one, I'm going to rewrite 60y is greater than or equal to negative 70x plus 600 and divide by 60. We get y is greater than or equal to negative 7/6 x plus 10. So the first one I'm going to do, x plus y is less than 15, looks like it's a dotted. Oh, did I do a dotted line for this one, by the way? I didn't. I'm so sorry. This last one should have had a dashed line here and a dashed line here. I apologize. Either way, it still satisfies what we have there, right? Totally does. My answer is still good. All right, so this one, we have to make sure to do some dashed lines in some places. So the first one I'm going to count for right now. 15 is in between. I wrote 20 and 10 wrong here. That is stupid of me. 10 is here. 20 is here. 15 is still between 20 and 10. So there's the first one. And 0, 0, for example, is away. If I drive 0 hours, my friend drives 0 hours, then that would be less than 15 hours. That would be good. So it's shading underneath this one, which is a part of it. The next one, negative 7/6 x plus 10. Now it's greater than or equal to. The y-intercept is 10. If I go down 7, it doesn't really fit. Let's go an official down 7. Here's 9, 8, 7, 6, 5, 4, 3. That's down 7. And over 1, 2, 3, 4, 5, 6, like that. At least I get 1 point that I can draw the line on before I kind of run out of room. It will be solid, and I'm going to end it when it hits right there. The x-intercept is kind of rando. Whatever 600 divided by 70 is. Kind of rando, but we will be above that one. It is a greater than or equal to. When y is by itself, we will be above that line. So somewhere within here, but my friend will drive more than me. Y is greater than x. The line y equals x is a y-intercept of 0 and a slope of 1, and this is a dotted line, dashed line, so we're going to go like this, and we'll shade above that one. And, of course, your friend has to drive positive amounts at hours, so I'm going to restrict us within this bound right here, or within this region. So our bounded region, or overlapping shaded region, whatever you want to call it, is somewhere within the confines of this area right here. So we need to come up with a solution that falls within here. So I'm going to pick and choose, and it can't be on a dotted line, and I think it's really important that we state that. So I'll pick and choose this one here. That's 2, 4, 6 hours here and 8 hours here. So 6, 8. So I can drive 6 hours. My friend can drive 8 hours. Let's make sure that that satisfies everything. I can drive 6 hours, and my friend can drive 8 hours. Okay. Is that less than 15 hours? Yes. Is my friend driving more than me? Yes. Did we travel 600 miles? If I drive 6 hours, that's 420 miles. If they travel 8 hours, if they go for 8 hours, that's 480 miles. 420 plus 480 is 900. That is more than 600. So yes, it satisfies them all. That's what I like about them. That's what I like about these problems. Sorry for not doing the dotted lines there before. It's fixed, and it was good anyway. Okay, number 37. How are solving systems of linear inequalities and solving systems of linear equations similar? How are they different? Honestly, there's not a lot that's similar. I mean, the concept of being on the same thing. So similar, two graphs on one set of axes. And that's kind of where the similarities stay, because for our systems of equations, we only care about the point of intersection that is the ordered pair. That's a solution. So the only other thing that I can state is that must be a solution to both, or to all equations, to all algebraic statements. I can't, equations / inequalities. Inequalities. Must be a solution to all of it. Now, what's different is pretty much everything else. Equations only contain the point of intersection. This is assuming it's one solution. I know there can be no solutions, infinite number of solutions. Point of intersection, and should be written as an ordered pair. And solution should be written as an ordered pair. Now, I'm not going to talk about they're also similar in that you draw lines with slope and y-intercept. That's clear as day. You draw lines. Whereas inequalities have some dashed lines, shaded regions, and the overlapping shaded regions represent the infinite number of solutions. Not just one, but infinite number of solutions available. Therefore, the graph is super important on that one. If you'll notice, I don't know if you have noticed or not, if you'll notice, we solved systems of equations not just by graphing. We also solved using substitution and elimination. We can't solve systems of inequalities using substitution or elimination. There isn't just one answer. The graph is the answers, the set of answers. You can provide an answer like I just did on the last couple problems. You can provide an answer, but that wasn't the only one. There were a bunch of other ones, and so it's an infinite number of solutions that you have there. There are no solution cases for both. I do understand that, and they have to do with parallel lines or whatever, but that's kind of where the buck stops for myself. But yeah, both can be done by graphing. I think that's the thing. It's two graphs, because here's the thing. Both can be done by graphing. So I should mention that. You can solve these equations can also be solved algebraically. Systems of equations can also be solved algebraically. Elimination or substitution. Inequalities cannot. That is a true difference. That is a true difference. Okay, number 38. How do you see it? The graphs of two linear equations are shown. I do see that, and that's how I see it as well. I don't know if you agree. All right, those are equations. Replace the equal signs with inequality symbols to create a system of linear inequalities that has point C as a solution, but not points A, B, and D. Okay, for point C to be a solution, keep in mind, these are just the boundary lines. We don't yet know, and here's it's part of the tricky part, we don't yet know whether they should be solid or dashed. Because I'm looking at you, point B, and they say point B can't be a solution. So for this to work, how will point C be a solution? Point C is a solution if this is my overlapping shaded region here. The overlapping shaded region here is bigger than this line, but it's above this line, but under this line. So this line, we need some sort of greater than. This line, we need some sort of less than. And actually, I can put them right here. So greater than, less than. I'll make sure to write them on my side in a bit. Does that work in total? It does as far as eliminating A and D, because this would be the overlapping shaded region. Does it eliminate B? It does, because this one keeps this as a dashed line like that, being just greater than. Can this one be less than or equal to and still be good as far as not including B? It can. So for the sake of this exercise, I'm going to do that. My answer for this will be y is greater than negative 3x plus 4, and y is less than or equal to, or you can put less than, 2x plus 1. And that's how I see it. Explain, I kind of said it out loud. All right, number 39, using structure. Write a system of linear inequalities that is equivalent to the absolute value of y equals x, where x is greater than 0. Graph the system. Write a system. So for this here, if you recall, the absolute value of y equals x equation would be either y can equal positive x or y can equal negative x. Now we learned, did we learn absolute value inequalities? I think we did, right? Okay, so shoot, I was going to teach it to you now, but yeah, we totally did, right? So absolute value of y is less than x. They said x has to be greater than 0, so we're only talking about ones that are solutions and where a positive or negative occurs. So y is less than x and y is greater than negative x is our setup for that. This goes back to chapter 2. I forgot that we actually did do these. But this is now a system. So in the system, the and is important in that we must stay within the overlapping shaded region. So there's our system. There's the writing a system, and they say graph it. So in terms of graphing this one here, we will have not something that small. Come on now, Mr. Robinson. Probably normal size is fun enough size. I'm kind of getting into the whole using black now only because you can only use pencil. I actually used to do that. I used to start in color and then I would go into going into black after that. Now y equals x is a slope of 1 and a y-intercept of 0. So I'm going to go pretty fast on these ones. And y equals negative x is a slope of negative 1 with a y-intercept of 0. So we're looking at these two. We have to be we have to be below this one and above this one. So this is our overlapping shaded region here. These are the y values that when we take the absolute value of them, we are between, we are within our x values that we can be. Sorry, I'm getting it set up. So there we go, like that. Here lies the overlapping shaded region only, right? Above this, below that. Now that I'm streamlining them more, now that we get more into these things here, right? Okay, number 40, making an argument. Your friend says that a system of linear inequalities in which the boundary lines are parallel must have no solution. Is your friend correct? Explain. My friend's incorrect. We've actually seen, let me find some. Well, those aren't parallel. That was no solution. This was not no solution, right? Number 26 was not no solution. Was not no solution. There was another one that I did. That's no solution. That's not no solution, I should say. This one. This one is the kind that I'm really thinking of. Above the bigger line and below the lower line. And this one is also no solution. So, absolutely not. See some of those other questions. Friend is incorrect is par for the course, right? So, number 40. I mean, they say explain, but they could overlap depending on which side of the boundaries they're on. So, my friend is incorrect, as overlapping shaded regions can still exist depending on what side of the boundaries they're on. The shaded regions are on, right? So that's kind of what we're saying there. It's only when like above this one and below this one, it's a no solution set, things like that. So, all right, number 41, critical thinking. Is it possible for the solution set of a system of linear inequalities to be all real numbers? Explain your reasoning. Yes, it is. If I'm... Oh, wait a second. I was thinking... No, never mind. I was thinking that we hit shading everywhere, but overlapping shading, no. Overlapping shading, no. Once we set a restriction, we have taken away some of our solution sets. So for inequalities, no. I was thinking of, and this just went back to a problem that we already had. Remember the x minus 4 one? I was thinking of that one and saying, hey, we'll shade here and we'll shade here. But that's not overlapping. So this, no, it is not. Once an inequality is created, we must be bound by its property, its statement, no matter the overlapping shaded region, how big the overlapping shaded region. So that's the idea there, right? Once you do that thing, you are now defined by it. Okay. So it's all about the overlapping. All right, 42 to 44 says, write a system of linear inequalities with the given characteristic. Number 42, all solutions are in quadrant 1. Well, that's kind of what I was doing a lot of on the previous, it says write a system. Oh, I thought it says write the system. So on number 42, I could do something like, if they're all in quadrant 1, that's kind of like what I was doing with the word problems, but being in quadrant 1 also means not being on the axes. So I could do something like this for number 42. If I could also just do anything within quadrant 1, so I could also do x is greater than or equal to 4 and y is greater than or equal to 7, something like that. So this works, but this is bounding ourselves within all points of the first quadrant. This is within, all points are within the first quadrant. There's kind of a difference in how I stated this. All right, number 43. Listen, either or is fine there. All solutions have one positive coordinate and one negative coordinate. This time I should bound myself in some sort of way like that, where I'm doing one positive, one negative. I think I'll not be so generic or so specific with zeros. I want to be more generic and just kind of throw it all around. So let's do one positive. Let's keep our x's, say, positive, and our y's negative. Let's keep, why did I write y first? Let's keep x greater than, say, 5, all positive, and negative y has to be less than some negative, less than or equal to negative 1. Something like that will work. Okay, number 44, there are no solutions. Well, to have no solutions, we have to be like above a line and less than a line, something like that. So we can do like y is less than, let's do like 3x minus 1. And then y is greater than, have to be parallel but above it, 3x plus 5. That would be an example of a system there. No solutions. That's a quick set. We have 4 more to go. Number 45, open-ended. One inequality in a system is negative 4x plus 2y is greater than 6. Write another inequality so the system has no solution and infinitely many solutions. Infinitely many is as long as it's as long as it's not no solution, really. You'll be fine. So we have negative 4x plus 2y is greater than 6. So for part A, here's the thing. I want to get something parallel to this, but also kind of on the other, kind of like this one. Parallel to this, but on the other side of it. So let's add 4x over and then divide everything by 2. And I got this guy right here, okay? So my thing that I need to be within this system is, if this is above this one, let's get parallel, and below it in some sort of way, 2x minus 3, like that, right? So that's a valid answer for it. Now, if I wrote it in standard form, I don't know if they wanted me to stay in standard form or not, but write an inequality, this one works. That would be my answer. Part B, I can write literally anything that has infinitely many solutions, as long as it's like different slope or something like that, right? So part B, I can do y is greater than or equal to 5x minus 7. That's all good. Infinitely many solutions is as long as it's inside the overlapping shaded region. Unless I'm reading it wrong, that's what it looks like to me. It's infinitely many. And that's the thing about these, right? It doesn't have to be on the line. It doesn't have to be parallel or, something like that. It's just whatever. It's open-ended too. Number 46, thought-provoking, also often open-ended. You receive a gift certificate for a clothing store and plan to use it to buy t-shirts and sweatshirts. Describe a situation in which you can buy 9 t-shirts and 1 sweatshirt, but you cannot buy 3 t-shirts and 8 sweatshirts. Write and graph a system of linear inequalities that represents the situation. Okay, this one's a little more open-ended than the last set where they gave us kind of things to guide us and bound us. Now we have to bound ourselves. So for here, I'm only in the first quadrant, but t-shirts, I should have probably been categorizing these the entire time, but I did define them, so I'm good. And sweatshirts. Okay, a solution I'll put in green, non-solution I'll put in red. So I can do 9 t-shirts and 1 sweatshirt. I can't do 3 t-shirts and 8 sweatshirts. 3 and 8. Okay. So I want to do a system, right? Obviously we'll be bound within the first quadrant, so I'm going to kind of state, positive, that's all good. So we have that in mind already. Let's now start talking about things that we can afford and how many we're restricting to and things like that. I want to do the one like with the friend thing that says like you want to buy more t-shirts than sweatshirts. So I'll come up with that part as well. So let's get it started by stating, that's my shape tool. Where's my text tool? Okay. T-shirts, let's see. You can't spend more. I'll make t-shirts $10 and let me do those first. T-shirts cost $10 and sweatshirts cost $20. Now, if I can do 9 t-shirts and 1 sweatshirt, that means that's $110. So I can stay within there. 3 t-shirts is $30. 8 sweatshirts is $160. So that's $190. So I can't spend more than $150. How about? You can't spend more than $150. And you want to buy at least 10 shirts. Okay, I'll just stick with that because that does satisfy this. I don't need to now buy more t-shirts and sweatshirts. So let's now construct that graph with this in mind. Let's write the inequalities from that. So t-shirts are clearly X, sweatshirts are Y, right? So X plus Y has to be greater than or equal to 10. So this one's going to be on the line. I hope you realize that. And then 10X plus 20Y has to be less than or equal to 150. Oh, what's my y-intercept there? What's 7.5? So let's do, okay, this is way too thick here. Let's thin that out much more. We know we're in the first quadrant. So 7.5 is my y-intercept of that first. I could do slope-intercept form, but I'm going to go straight into it. So 7.5 up to 15. Oh, wait a minute. 15 is way off the mark there. Somewhere over there, right? 11, 12, 13, 14, 15. Okay, we need to stay underneath this one in terms of cost. So green is underneath, red is not. That's what doesn't satisfy that. But I need to buy at least 10. So this one's on that line right there, right? So where my overlapping shaded region, this, sorry about the scaling and stuff, I kind of screwed it up. But this one here would now look like this. So I satisfy it just on the border right there. I could also buy a few more t-shirts if I wanted. I could buy 12 t-shirts and 2 sweatshirts and still stay under budget because that's $140 and that's at least 10 t-shirts. So anything there works. There's my open-endedness. Okay. Oh, received a gift certificate. So let's see. My gift certificate says I cannot spend more than. Let's say you have a $150 gift certificate. Okay. Okay. There's that one. Let's go to number 47. Critical thinking. Write a system of linear inequalities that has exactly one solution. Okay. Now, that means we can do more than 2 inequalities, which is the way that I'd want to work that out. So my way to do one solution, because what did we see before? Anytime we have an overlapping shaded region, it's going to be infinite, right? So the way I can do one solution is if I do 3 of them. I'm going to make them easy. I'm not going to do like this whole 1/2 x whatever. In fact, we can do vertical and horizontal lines, things like that. So here's the idea. If I did something like x is greater than or equal to 1, y is less than or equal to -3, things like that, then suddenly my graph has an overlapping shaded region, right? It's got these two. X is greater than or equal to 1. Okay, maybe I'll do one diagonal one. X is greater than or equal to 1 is right here and to the right of 1. Let's actually get arrows back here again. Bring them back and thicken it out. I will keep it black though. X is greater than or equal to 1 is to the right of 1. Y is less than or equal to -3 is underneath that there, -3. And I'm doing these or equal to's. That's actually kind of important for this thing. Otherwise, points on the boundary line won't count. But right now, my overlapping shaded region looks like that. It's infinite. The only way for me to really get one solution is if I just nick a single point, which is maybe this one right here. But I want to do one that doesn't get in the overlapping shaded region. So let's do something where I cross through here like that. Like actually, I can do a slope of 1, but cross at -4 like that. So what would that be? But I have to be above it. Y is greater than or equal to, let's say, x minus 4. That way, this line, slope of 1, y-intercept of -4, I will be going through here. Let's keep that slope of 1 on, like this. We would shade above this one, but what happens when we are below? What happens when we're supposed to be below this one, this set right here? Hold on, I'm trying to still fix this. Man, did I not put my slope of 1 right? I don't think I did. There we go. What happens when I go? Having trouble here, guys. Maybe this line isn't perfect. There we go. What happens when I would be in this overlapping shaded region here, but suddenly there's a shaded region right there that's above it? Suddenly there's no overlapping shaded region except for what's on the boundary line itself. So all these being solid lines means this is the only solution to this that satisfies it. 1, -3. And let's double check those and see that they work out. Is 1 greater than or equal to 1? Yes. Is -3 less than or equal to -3? Yes. And is -3 greater than or equal to 1 minus 4? Yes. And that's the only set that would satisfy all 3. Once I hit 2 -3, then it doesn't satisfy this one. You know, once I hit 0, 0, it doesn't satisfy either of these. So this is one, it's open-ended, but this is one that works here. They have to be solid. I think I need at least 3 inequalities. I think I would need at least 3. And there's one that would work. Now there are other ones I can do, like just 2 parallel, two lines that are on top of each other. Y is greater than, Y is less than or equal to here, and X is greater than or equal to, X is less than or equal to here, and we'd be good as well. But I'm going to try it like that. All right, number 48. I think this is the last question, but it's a lot of parts. Have we gone 2 hours? Oh, almost. All right. Number 48. You make necklaces and keychains to sell at a craft fair. The table shows the amounts of time and money it takes to make a necklace and a keychain and the amounts of time and money you have available for making them. Write and graph a system of 4 linear, so they tell us 4 linear inequalities that represents the number of X necklaces, so they define it, and Y keychains that you can make. Okay. It takes half an hour. It takes 30 minutes to make a necklace, 15 minutes to make a keychain. You have 20 hours available. So my first set that I can do here is 0.5x. That's the number of hours making necklaces, plus 0.25y. I have 20 hours available to do that. I have $120. This is my cost to make. This isn't the amount of money I make, but I'm doing these at a craft fair. So it costs $2 to make a necklace times the number of necklaces, $3 to make a keychain times the number of keychains. We have to stay within 120 there. I can't think of any two other restrictions that they didn't mention any two other restrictions. I can't think of any two others other than the ones that I've been stating that have been implied all along. We must have a positive, or we can't have negative necklaces and negative keychains. To me, these are the only other two that I should write. So unless I should have been writing it each time, I'm at least going to be doing that here. So that's my part A to me. Well, that's the portion of it. Now I have to graph them. In order to graph these, I have to come up with intercepts, or I can. These intercepts are clean. My x-intercept here, divided by 0.5 is times 2, so it's 40. My y-intercept times 4 is 80, so I can do that one. And then my x-intercept here, I guess I'll do different colors for now, is 60 divided by 2. And then my y-intercept is 40. So I can get those ones. And of course, these are just bounding us within the first quadrant. Let's get another one of those first quadrant graphs. I got to find one. That was a whole one. Here we go. Let's get one of those first quadrant graphs. We'll change our scale. Whoa. Come on. I hit the copy button. Now I have to go all the way back. Let me make sure that it actually copies this time. Copy. Paste. There we go. Okay. Sorry about that. You've seen that happen on my stuff before. You hear me hit Control V, and I can guarantee you it was or Control C, and I can guarantee you it was Control C. Okay, so X is number of necklaces, Y is number of, well, it doesn't matter now. Now we're just graphing. So 40, 80, let's just go to 100. So 100 here, 50 here, 50 here, 100 here. Okay, so X-intercept of 40, Y-intercept of 80. And we are bounding ourselves by the zero spots, right? I've been doing that the whole time. I've just not been writing it every time. I've been stating it, not writing it. So let's do intercepts here. Now, if you'll notice, it does say less than or equal to 20, and that when you plug in 0, 0, it would satisfy it. We would stay underneath this one. We also have to stay underneath this one with an x-intercept of 60 and a y-intercept of 40. So, but there's an overlapping shaded region that we have to stay, again, under, because 0, 0 works there. I can spend $0 and still satisfy the set of what's available. So there's that one as well. Now, the other two are, of course, bounding us within this first quadrant. I don't know why this is our first time that they're kind of telling you that. You know what I mean? They should have been telling us that kind of the whole time, or I probably should have been writing it the whole time. Maybe it's my fault, not theirs. So we're staying within this set in here, okay? So let's go ahead and kind of mark that up. Shade it all up. I'm trying to thin out the transparency. All right. So here's our set we can stay within. Now I don't know some exact points on the lines because the scaling is by tens, but we'll see what they ask next. So there's part A as a whole. Part B, find the vertices of the graph of the system. Okay, so this is 0, 0. This is 40, 0. This is something called linear optimization, sort of. We're not doing objective functions, but this is 0, 40. Now, what's that next one? Is that right on this point right here? Should I make that assumption? I think probably it's kind of fair to say these slopes are like down 2 over 1, down 2 over, so it's hitting there, and this is like up 2, left 3, up 2, left 3. So that's probably right on that. That means it goes by 10s and 20s. That's 30, 20. What you could also do is you could set this equation equal to the, yeah, if we got y by themselves, you could do y equals mx plus b and set those expressions equal to each other, solve the x. That's a little overkill for this if I think that's the actual point right there. That's 30, 20. Part C, oh, this is an objective function. Okay, this is something called linear programming. You sell each necklace for $10 and each keychain for $8. The revenue R is given by the equation R equals 10x plus 8y. This is known as an objective function. Find the revenue corresponding to each ordered pair in part B, which vertex results in the maximum revenue. Okay, this is a brand new thing. They're not teaching you, but they're just kind of using this based off of it. Keep in mind, these are parts of the overlapping shaded region. These will be solutions. There's something called linear programming, where you can find the maximum or minimum of something based off an objective function, and it will always occur at a vertex, at a point of intersection. Clearly, 0, 0 will not maximize your revenue. Wait. This is cost to make. Is cost to make the same thing as revenue? Okay, I'll pretend like the higher the number, the more maximum revenue, stuff like that, right? When it says cost to make, maybe that's how much we're selling it for. I don't really know. Anyway, oh, I'm sorry. This is revenue right here. Duh. Okay, so anyway, revenue is based off of this. Do we have to subtract? Oh, it's revenue. It's not profit. It's not profit. It's not profit. Okay. Anyway, clearly 0, 0 will not maximize revenue. So when I try 0, 0 here, I get 10 times 0 plus 8 times 0. I make $0 in revenue. That didn't maximize it. Let's try 40, 0. Here, the revenue will be 10 times 40 plus 8 times 0, which is $400. It's a lot of revenue. I don't know how much it costs. They didn't ask for profit. 0, 40 is R equals 10 times 0 plus 8 times 40, which is $320. And then 30, 20, it's always most fun when this is the one, although it gets a little redundant if it is as well. That's why if we had multiple points of intersection, that'd be cool. Let's see. 10 times 30 plus 8 times 20. That's 300 plus 160, which is 460. So this one maximizes revenue. So which vertex? 30, 20, which is 30 necklaces. If you make 30 necklaces and 40 keychains, $20 keychains, you will you will maximize revenue. And the idea, once again, is it can only occur, and I'm telling you this straight up, I'm telling you right now, it can only occur at a vertex within the shaded region at which they're bound and whatever. It won't ever be, even if it's on, obviously it won't be within, because you can always maximize it by going higher, but it will never be on the boundary line itself right here. It's always at a vertex. Which one is the test that you do? And you should test them all. Obviously 0, 0 is not going to do it, but you should test them all and see which ones, in this case, the 460 ended up being it. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching, and that concludes Chapter 5, outside of review and cumulative assessment, of course, but that's the test and cumulative assessment. But that's the learning portion of it. Now we got to get to the reviews and such, and systems of inequalities are a part of it. I like the word problems. I don't know if you do, but I do, as far as, like, there's work to be done, but it's cool. It's cool that this visual tells you what we can do and can't do when it comes to solutions, especially for real life application. I like them personally. And I hope you did as well, or at least I hope you learned it and understood it. And we get to review. So thank you so much, guys. Take care. I'm going to see you in that next one.